Alright, so I decided to make a video of a lot of the stuff that I learned. I don't want to go crazy into detail on some of the stuff because there's a lot. Uh, but just a general, like, as a meteorologist, where they start from, things, and just like some basics on understanding, like, looking at the forecast models and why they can be tricky. And my focus and everything that I've learned on is severe weather. I don't care about snow. I mean, yeah, I'll watch it when it's coming down in other places, and obviously I'll pay attention to the weather when we get it here. But like the focus of everything that I've wanted to learn has been mainly severe weather. I still know a lot of other things, but this is just what I've learned watching stuff over and over and over again and listening to tons of different meteorologists and just doing whatever I can to understand. Because when I lived in Michigan, and I know how a lot of people in Michigan are, probably how I was when I was like, well, whatever, they're calling for storms to be bad, but I've never seen a tornado before. We don't get them. Well, you do. It's just, on average, it's only like 16 a year, which I think this year you're already at 28 or something. So it can be higher, it can be lower. It's just that's the general average of tornadoes that you get in a year. And to be weaker too. I'm sure you've gotten an EF3, an EF4. I'd have to go back and look. I know so much. Like I've went and seen so many tornado events and look up the footage and when and where. It all blends together, so it's hard to really pinpoint when this happened and where it happened. I just, after you watch so many, they all really blend together. So I'm gonna talk a little bit about weather patterns, not too much. Like I said, where do the meteorologists start at? I'm not going to go into crazy detail at all the things that you can look at when it comes to looking at short range models, medium range models, and long range models. I'm just going to keep it simple. And then I'm also going to try and show some things on how you don't have to be a professional to understand the radar. It's really not too complicated. And just other ways that you can look at while you're watching people cover the weather, where you can go, I can see what they're pointing out at, and now I understand. And now, even if they're not there, I can look at the radar and maybe I can go, well, yeah, there might be something here, because I've seen stuff that has not been issued by the National Weather Service that end up being issued by the National Weather Service, where I caught it before they did, or maybe they just, because there's a lot going on, maybe they just didn't get to it or didn't see it at the time, and then they're like, oh shoot, we should warn this. So if you watch it enough, you don't have to be a professional. You watch the radar enough, you start picking up on a lot, and you can catch stuff before the National Weather Service does. And as I decided to make this video, I was watching the weather. We had some storms here today, but nothing bad. And right now there is a tornado warning in Minnesota. It's got 16 minutes left on it. Tennis ball sized hail. That's pretty big. And you can see the purple through here is the hail. So there's quite a bit of hail, and it's really large hail falling. If you look at the velocity, which to me, I mean, at some point it looked like there's a short window of where it looks somewhat decent, but for the most part, it's still pretty broad. You see the red and the green on top of each other like this. The red, let's look for our radar station so we're really far away from the radar station. Radar station's down here, and our storm's all the way up here. You can see the red and the green. The green is what's heading to the radar, and the red is what's going away. So you can see the storm up here. You have the red and green on top of each other. That's what's going to the radar and what's going away from the radar, even though the storm is moving this way. Which there's a little bit of rotation up here too, but it's pretty broad. So it's hard to tell when you're so far away from the radar how great the data from that weather station is. It's just so far away, so it's harder to read. So when you look at this, you can clearly see the red and green. You can see the rotation like this. That's counterclockwise. That is a right motion storm vector. You can get tornadoes out of left motion storm vectors, and you can get tornadoes out of right motion storm vectors. However, the left motion is rare. I think one happened a few months ago in Texas, and the right one is more so your tornado maker. You can get them out of both, but usually meteorologists look for the right motion storm. So you see the counterclockwise spin. There is rotation, but it's pretty broad. It was still enough for them to play it safe and issue a tornado warning. Another way, just by looking at the radar, not having someone on the ground, is, you've heard it before if you've watched the weather, is called the correlation coefficient. And that's rain and hail are relatively the same as they fall. They can come in different sizes, but they correlate with each other. So they blend in pretty well. On the correlation coefficient, you're looking at what's being possibly lifted up into the air. So you can tell that, okay, there's hail and rain. Rain comes in different sizes. But you look at the correlation coefficient, it still all blends in together. What you're looking for is stuff that's not the size of hail and rain. Tree branches, shingles, siding, yard decorations, anything that can get lofted up into the air that's not the size of hail and rain is what you're looking for on here. And it's another thing that the further you are away from the radar, the harder it is to determine how well that data is. And looking at this, I would say that there's nothing on the ground, but it's just really hard because it's so far away. You can also compare it to the velocity and look where the velocity is on the map and compare it with if there was a debris signature, does it match where the velocity couplet is? And like I said, there's not really tight rotation. It's pretty broad. You're not going to get a tornado out of really broad rotation. You want to see it tighter, and I'll show examples of this later in this video. But where the rotation is, and then where you would see a debris signature if it were on the ground, this doesn't look like a debris signature. It just doesn't. And this is hard. I'm still learning a little bit on the correlation coefficient because it's really tricky. Sometimes it's like, oh yeah, I can clearly tell what that is. Sometimes it's like, well, I'm not sure. It's just a real tricky thing. But it's a way, without having a storm chaser or anyone on the ground, to where by the radar you can go, yeah, there is something lifting up debris and launching it into the air high enough to where you can see it on the radar. All right, starting out, a low pressure and a high pressure system. A high pressure system is convergence aloft and divergence, or going away, below. It's allowing cool, dry air to fall and get to the surface and then heat up. And that's how you have your nice, sunny, beautiful days. Obviously sometimes can be cloudy or partly cloudy. And your low pressure system is convergence below, coming together below and divergence aloft, spreading apart aloft above our heads. And these aren't like these aren't winds that are coming straight down and going straight out, or coming together straight and then going straight up and then going straight out. They're rotating, and that's because of the Coriolis effect. And that means it's because the Earth is rotating that these winds aren't going to be moving just from the surface and up, or coming up aloft and coming down to the surface below in a straight formation. Because the Earth is rotating, they're going to be rotating as they come up and down. Sorry if I flinch. That was another tornado warning. It's like hearing that alarm on my app. Every time I hear it, I just like, what's going on? Where is this happening? But also, a low pressure system is causing, it's forcing for ascent. It's forcing that hot, humid air and lifting it into the atmosphere to cause convection or storms. So that's how a low pressure system works, and how we get our rainy days and sometimes severe weather from a low pressure system. Alright, so what meteorologists usually first look at is the 500 millibar. This is the 500 millibar. This is looking at what the jet stream is doing. There's three types of troughs. This right here, what you're looking at, is a negative tilted trough. If you draw an axis across, it's negative. There's a negative tilted trough, a neutral trough, and a positive trough. The negative is normally the bringer of the most severe weather. That is your tornado, damaging winds. The other two can, it's just this is normally the worst one. This is the worst of the trough. This is what a neutral trough looks like on the jet stream, in the jet stream on the 500 millibar. Like I said, it can also cause some severe weather. It's just the forcing and the way the geometry of a negative tilted trough is, it causes way more forcing for ascent. But this is what a neutral trough looks like on the 500 millibar. And then this is a positive tilted trough. See how the axis is different. You have the neutral, which goes straight down, the negative, which the upper part is towards the west and the bottom part is towards the east. And a positive tilted trough is just the reverse, where the out of where the trough goes down to eject is pointed further towards the east, and the bottom is pointed towards the west. And this would be your low pressure system in this area, and this is the way the axis is set on this. Which, like I said, all three can bring severe weather. It's just the geometry of a negative tilted trough is the one that causes the most forcing for ascent for the most severe weather. So on a negative tilted trough, it's almost like if you can imagine a water hose. And you were to pinch the end of the water hose so the water stops coming out, and then you were to let it go some to where it builds the pressure up, and then it just launches water everywhere. How you get your water pressure, or the end of a hose, a spray hose on a garden hose. You pull the trigger and you can change how it spreads across. It's how a negative tilted trough ejects, is you have convergence coming together, or confluence, and then you have difluence. So you have coming together and then coming apart. So in the same way, it's like bottlenecking. If you were to take a 2 liter and you were to shake it up, and then you were to spin the cap off real fast, and the soda just sprays everywhere, it's kind of the same aspect. You have You have confluence coming together, this pinch point where you have your hose pinched off. You have diffluence where it goes all over the place. And on a negative tilted trough in a low pressure system, so you draw your axis across this area where it's kind of pinching itself off. You have convergence coming together, and then you'll have diffluence, which is going away. This is what causes the forcing for ascent and lifts that hot, moist air to create storms, convection. And Mother Nature doesn't like this void, so she fills the void with convection. Alright, so now what I talked about a little while ago about left motion and right motion storm vectors. Now, how they find out in this trough, in the jet stream, this storm system that is going to be coming, or forecast to be coming, how the jet stream is literally like a river of air. And this is how they find their right motion and left motion storm vectors. You have a river, right? And in the, let's say the middle of the river is the strongest current. If you were to take a metal pole and drop it down in between the bottom, the middle of the river where the strongest current is, and the edge of the river, you're to drop a pole down. Which way is the current going to wrap around that pole? The current's going this way. It's the middle of the river. You drop the pole down in between the edge of the river and the middle of the river. The current is going to wrap around this pole, like this. That would be your right motion storm vector. You do the same thing between the middle of the river, where the strongest current is, and the bottom edge of the river. Drop a pole down in the water. Which way is the current going to wrap around that pole? Like this. That's your left motion storm vector. That's how they find their right motion and left motion storm vectors. Which way the current would wrap around the pole in a river. Your right motion storm vector is your tornadic type. It's the one that produces tornadoes the most is a right motion storm vector. A left motion storm vector can produce tornadoes, but they're rare. Like I said, I think one happened a few months ago in Texas. So they can happen. It's just this is what they're normally looking for. Obviously, if they see rotation and it's moving in what would be on the radar clockwise, right motion would be counterclockwise, left motion would be clockwise. If you were to look at a radar and look at the velocity to see the storm rotating. They would still obviously keep an eye on it because it's still a potential that it could produce one, but it's your right motion storm vector is the one that normally produces tornadoes. Alright, now on a negative tilted trough in a low pressure system, to find those storm motion vectors is, like I said before, you draw an axis on the way the trough is tilted. And you can find your right motion and left motion storm vectors. That's hard to see. And that's how you can tell that this storm is, this system is capable of producing tornadoes. Another tornado. Where is this one at? This one's observed in Clear Lake. Let's look at the velocity on here. Man, even that's hard to look at. Oh yeah. rotation's right here. You can see it spinning counterclockwise, so it's a right motion storm. Now let's see if it is on the ground. I don't know. Oh no. Maybe, hopefully it hit north of town, which it looks like the rotation was north, but there's also Alderman. This is right before, this is right in South Dakota before. Oh, what am I doing? Split screen. Velocity. And see, this is one of those things where it's hard, where here's your rotation here. So you would be looking for a debris signature through here. And it's that doesn't look very promising. But this is also, this is on the ground. This is out in the middle of nowhere right here where the rotation is. Also with these troughs, they can be big troughs and cover a lot of states and cause widespread damage, but there's also what's called a shortwave trough. And they're the same thing, they're just smaller troughs and they don't cover a huge area. So they might only affect one state or two states. So you get these big bowling, they say bowling ball troughs like this, and you can also get little troughs that move across the U.S. They same, no difference except how much ground they cover. A shortwave trough will cover a smaller area. A giant bowling ball trough will cover a greater area. So that's why I had these other pictures of the troughs in a smaller form, is that they can come in big troughs and little troughs. So in the springtime, this is what the trough, the jet stream, likes to do. It likes to do the worm or the wave, whatever you want to call it, and it likes to just bring, or a rubber band. It just wants to keep creating trough after trough after trough. That's why in the springtime we get so much severe weather. We can get troughing in the summertime, but it's a lot of zonal flow, and zonal flow will look like this on the 500 millibar. It'll be just straight flow. There's not going to be a whole lot of troughing, even though little shortwave troughs can appear, and you can still get some troughs in the summertime because we still get tornadoes in the summertime. We still get severe weather in the summertime. So some things that can change, make or break an event from being really severe to not as severe as they forecasted. And that is prefrontal convection and cloud cover. And it's self-explanatory. They could call for an area to not have, they say that the bad storms are going to come in the afternoon, around 2 in the afternoon, and they forecasted for clear skies out ahead of it. So the sun was going to have its time to really heat up the surface and really destabilize the environment. So the storms that are coming into that environment later in the afternoon or sometime in the afternoon, whenever they forecast it, are going to have that extra buoyancy. So we all know that heat rises. Heat rises faster through cooler air. So as you go further into the atmosphere, the air is getting cooler. The atmosphere is cooler going up. And the rate at which the air cools is at negative 9.8 degrees Celsius per kilometer. is what the rate that the air cools. So heat rises faster through cooler air, which I'll get into talking to that here in a little bit. Mixing, that is giving storms a mixed layer convective available potential energy. So it's giving these storms energy in the way that they're mixing as they're going further into the atmosphere. But prefrontal convection or cloud cover is they forecast that they're looking at the computer models, and the forecast models aren't showing any rain happening in the morning, any convection, or any cloud cover. They're predicting clear skies. So the sun is going to rise and be able to really heat up that surface that these storms are going to go into. So the storms that are going to be going into that environment are in a very destabilized atmosphere. And so you have storms that end up popping out that weren't forecasted, will block the sun from rising, block the sun from really doing its job on destabilizing and heating up the surface, which is giving, what you see here, is giving lift to the storms and giving them that extra buoyancy to climb further into the atmosphere to become mature storms. Small storms or baby storms, however you want to call it. A mature storm is 25,000 feet or higher into the atmosphere. Once a storm becomes mature, that is when it has the capabilities of producing damaging winds, hail, and tornadoes. If the storm isn't mature yet, I mean, it's still going to cause rain and lightning, but it doesn't have those capabilities yet of being able to produce the real nasty stuff. So because the models are never perfect, things like this can happen that can change how well the sun is going to give extra energy and buoyancy to these storms, and it can change the outcome of how severe the event could be, because they're computer generated models, given that a lot of them are really good and they just keep getting better. They're still never going to be perfect. The weather, no matter how hard we try to predict the weather, we're never going to be able to predict it fully, I think. So this is just two outcomes: cloud cover that can block out the sun, and prefrontal convection, storms that happen throughout the day and keep an environment cloudy and blocked off from the sun, is blocking off some of these storms that are becoming that are going to be coming later, stopping their potential for extra energy and extra buoyancy, extra lift. So another thing that can change, make or break, or put storms on the decline are outflow boundaries. And outflow boundaries, you have your low pressure system, and a low pressure system, especially in the springtime where you have cool, dry air coming down from Canada and Alaska and sweeping across the U.S. And then you have a high pressure system where you have your hot, humid air meeting up with this cool, dry air, a cool, dry line of air meeting up with this hot, moist air. And in your negative tilted trough, causing the forcing for ascent, is creating this convection. You have this cool, dry line. So the storms start forming ahead of this cool, dry line in this hot, moist environment. What can happen is the speed of the storms. The storms moving from the west east can be moving at a certain speed. They cause the forcing for ascent, causing these storms to form, and then this cool, dry air meeting up with this hot, moist air, where it is creating the convection, it's creating these storms. This cool, dry line can sometimes catch up with the storm and outrun the storm and cut the storm off from having that hot, moist air to feed off of. So I hope you enjoy my first grade drawing, but so storms and tornadoes are a lot like an engine. At least what I compare them to is that an engine needs air, a good air and fuel mixture to run right. And they also need to get rid of that, is it carbon monoxide, the exhaust. So storms and tornadoes in particular need a delicate balance of inflow, is what they're taking in, that they're feeding off of that hot, moist air, and outflow. Just like an engine, you have a lot of oxygen, you have a lot of air, but you have little fuel. Your motor's not going to run right. It's not getting enough fuel. It's not going to run properly. Same way with an engine and the exhaust. You block off the engine's exhaust, it's going to backfire. It's not going to run right, and it's going to stall or die. Same way with fuel. You could have a lot of fuel getting put into a motor, and it's not getting enough air. It's the air to fuel ratio isn't right. It's going to flood. It's not going to want to start. It's not going to want to run right. So I compare tornadoes in my head to engines, and where they need that delicate balance of inflow and outflow. Just like a motor needs a good fuel to air ratio, and they need the exhaust to work for them to run right. And so these storms that feed off of this fuel, that feed off of this fuel out in front of them, I meant to do what? To run out in front of them, to feed off of and ingest. If the cool, dry air gets ahead of the storms as they're moving from the west to the east, and that cool, dry air cuts the storm off from that hot, moist air, it's killing the storm off. It's killing its fuel. It's making this motor run wrong. It doesn't have a right mixture. And that's when you'll hear storm chasers, or if you watch a meteorologist live that are covering the storms, and they say this storm looks outflow dominant. This is what they mean. This means that the storm is no longer getting good inflow. It's no longer ingesting that hot, moist air. It's getting cut off from it. So now it's crapping itself out, essentially. It's losing its fuel. Another form of outflow boundary that can happen is rain-cooled air. And what that is same thing, it's low pressure system. The storm is moving from the west to the east, and it's feeding off of this hot, moist air. And then another thing that can happen is that rain-cooled air can get ahead of the storm itself, fall and get ahead of the storm, and that is another way that the storm can basically cut itself off from that inflow and no longer be able to feed on that fuel that's in front of it. So it's just another form of outflow boundary, and you can see this on the radar. You'll see storms moving on the radar, and you'll see a little thin green line that kind of forms out in front of the storm as it's moving when you're looking at the radar. And that's just another outflow boundary that can kill a storm. So that the storms will be on the downtrend once they start having that rain-cooled air come out in front. The rain-cooled air will start cooling and just pushing away that fuel away from the storm. So the storm kills itself out. Because of the rain-cooled air, it no longer has that fuel to tap into. And another thing that can affect potential for tornadoes to be possible or hinder the possibility for a tornado is cloud base. If you have a lower cloud base, you've heard the path of least resistance. You have a lower cloud base, a storm that's starting closer to the ground. It's going to be easier if the storm is coming into an environment that has the potential for tornadoes. It's going to be easier for a storm to spin, rotate, and then make it to the surface and create a tornado. You have a higher cloud base that's way further from the ground. It's going to be harder for a storm to rotate and then try to make it all the way to the ground to produce a tornado. So your cloud base, if it's lower or higher, can change the outcome of a storm's potential to be able to put a tornado on the ground. This is something I don't know if you heard as a theory, or people think this too, that, oh, tornadoes don't happen in the mountains. They can. It's tricky because it's a yes and no kind of thing, and I'm not sure exactly why. I still need to learn more, but like, in my mind, it's something about maybe that has to deal with the sun heating up the atmosphere, and in between the mountains it might be harder for that environment to be destabilized. I'm not sure. I just know that this is a tricky question because tornadoes can happen in the mountains, and they've happened in Colorado in the mountains 10,000 feet above sea level. But there is some element to mountains that can sometimes hinder tornadoes too. You think what we just talked about is having a high cloud base and a low cloud base. You know, the path of least resistance for a tornado to be possible. You have a low cloud base and a high one. If a low cloud base moves into the mountains, you know, it's the same thing. It's really close for a storm. If it wants to put down a tornado, it can. And if you have a high cloud base storm, you have it traveling into the mountains too, and now this also becomes a low cloud base. So now it's going to be easier for the storm to make a connection because now it's going in an elevated environment on the land, where now the storm is closer to the ground than what it would have been being in the flat surface or in a valley or something. So tornadoes or mountains can affect tornadoes and their potential, but tornadoes can still also happen in the mountains. Like I said, it's tricky. I don't know everything about this yet either, and I would like to learn a little bit more. But that's just another theory that people say, oh, we live in the mountains so we don't get them. You can, but there's something with mountains that can also change the outcome for the potential for tornadoes. Another thing is called the cap, and that's just another thing that can affect thunderstorms from having their severe potential or not. And capping is pretty simple. It's just, instead of warm air being just at the surface, warm air is further above our heads. There's a deeper or taller layer of warm air above our heads. And what happens is that your storm starts out in that warm air instead of above it. So because the storm starts off in the mix of that warm air, the storm is cooler than the air around it. So the storm struggles to climb and become a mature storm and have its capabilities of being severe. So when they say these storms should be somewhat tame because they're capped or there's a lid on it, it's that these storms are starting off in that mix of that warm air, and they're going to struggle to climb and get above that. And if you ever hear them say the cap is broke, so now these storms can tap into anything that they want to tap into, given the environment that they're in. It means that they fought through that. These storms fought through that warm air and got out of that layer of warm air, and now have the ability to climb and become mature storms and become severe. Storm mode and storm mergers can also affect how severe storms could be, or it can kind of ruin storms. Sometimes storms can save you from putting down a tornado because of storm mergers. And we'll start off with the jet stream in the way the speed of the jet stream itself, the wind speeds in it when it creates a trough. If the wind speeds are stronger or faster, or the wind speeds are slower, they can change what type of storm mode that you get. So in a trough, you have a negative tilted trough, or any type of trough, and in the winds, if you have winds that are slower in this trough, 30 knots to 50 knots, it tends to make more of a parallel storm mode, where storms are going to be firing off, and they're going to be by themselves, which means they're going to be able to tap in on more fuel. They're not going to be fighting with other storms for that fuel. They're going to have, it'd be like lighting a match in an environment with 100% oxygen. It's just like they have the chance to explode and really feed off of all that fuel around them. So when you have a slower moving trough, slower wind speeds, the storm mode tends to be parallel. They're moving from straight west to east. If you have a higher winds, stronger winds in this trough, in the jet stream, that's more forcing for ascent, and 50 knots to 100 knots. I think I've even seen 115 or something knots wind speeds in the trough. That leads to a more perpendicular storm mode. So storms are going to be merging with each other, and I'm covering perpendicular storm mode. Storms are going to be firing and merging with each other and clashing. So they're going to be fighting for fuel. Sometimes it's going to be hard for them to get their act together because they're constantly bouncing between other storms and also fighting for that fuel. So storm behavior is pretty wild to me. It's pretty fascinating too, and it's still something that they're working on learning more about meteorology and science with the weather, is that storm mergers can affect the outcome of a tornado being on the ground or canceling a storm out from creating a tornado. So you can have a storm that's became a mature storm. It started rotating, and now it's trying to put down a tornado. The formation of the storm has got its tornado supercell shape. It really wants to put a tornado down on the ground. And what can happen in storm mergers are when storm cells are clashing into each other, this storm could be trying to put down a tornado, and what happens is this other storm catches up with it, and they merge, and all of a sudden, for whatever reason, it trips the storm up. The storm is like, I'm ready, I'm going to put a tornado down now. I'm going to start rotating, and then another storm can come up behind it, catch up with it, they clash, and then all of a sudden the storm is like, what was I doing? Huh? What's going on? And it can trip the storm up, and now the storm has to pick itself back up. It's got to get its act back together to try then again get the shape that it wants to get, and it needs to get, and start rotating again to put a tornado down. So sometimes storms can save you by storm mergers, where a storm might be like really close to being able to put down a tornado, but then another storm cell comes behind it. They clash together and merge, and it trips the storm up, and now it's got to try again. And that's, like I said, that's fascinating. That's to me, that's crazy. You know, if a storm's in the environment where it's got the wind shear, it's got the instability, why would another storm just trip it up to where now it can't put down a tornado, and now it's got to recycle? And in the same aspect, storm mergers are good. They can also be bad, because there's a guy I watched, Cameron Nixon, that he's got a PhD in, I don't know, maybe physics, but he's got a couple YouTube videos where he talks about this storm behavior. In the same way a storm can save you because of storm mergers, storms can merge, and that might be for the worse, because like I said, tornadoes need a delicate balance of inflow and outflow. Storm might be struggling with that inflow or outflow, where it doesn't have that delicate balance, and then another storm merges with it, and it gives it a nudge into where it just perfectly aligns that delicate inflow and outflow, and then it nudges the storm into the mode to where it goes, okay, thanks, now I can put down a tornado, and it forms a tornado. So storm mergers can be good or bad, just depending on the environment and what's going on. But it's just another thing that where storms can save you, or storm mergers can save you, and storm mergers can be bad. It's just another thing that I find fascinating, but can also change the outcome of how severe an event is going to be or could be. This is another storm mode that there's multiple ones. They're just called a linear system or a quasi-linear convective system, QLCS. It can go both ways as far as changing the severity of a storm, because if you have storms that are firing off by themselves, like I said earlier, they can feed off that fuel. Once they turn into a line, now that whole line of storms is going to be fighting for that fuel. So in a good way, that might hinder the possibility for strong tornadoes, because now it turns into a line segment to where now this line of storms is all fighting for this fuel. At the same time, it said it goes both ways, because now this line of storms starts racing across, and they can cause quick QLC tornadoes, quick spin-up tornadoes, which are usually brief, and they're not very strong, and they're not long tracked. So this is another storm mode or setup that can go both ways. If it stayed into mode to where storms were firing off, they'd be able to feed more off that fuel by themselves, then they could have a higher tornado potential. But instead, the storm mode turned into a line and started moving across. Now that whole line of storms are fighting for that fuel out in front. So now the strong tornado potential has gone down, but there's still the tornado potential there. They're just going to be brief, quick, spin-up tornadoes that usually aren't very strong. So it's just another type of storm mode that most of you've heard. If you've been on this planet for a while, most of you've heard this quite a few times that they talk about. Okay, I'm going to try and keep this brief too right here. But what makes forecasting so tricky is that you can never look at one model. You kind of have to decipher between multiple models to find which one seems to be. You're always looking for the least aggressive or the least progressive forecasting model when you're looking at it. And you can never really just look at one. Like I said, you have to look at multiple. What makes it tricky is one run might look crazy, the other one might be the complete opposite, and then you find one that's kind of in between. The GFS is a long-range model. The ECMWF is an ensemble model, and it takes I think 19 different models. It blends them all together, so you can sometimes go, this model looks a little crazy, this model looks a little crazy. This one is kind of showing both and merging them together. Maybe this could be more likely the outcome of what's going to happen. But there's a lot of little things, like the NAM is a medium range model. It goes within like 5 days. So it's about a week out that you can look. Your HRRR is a short run, very short run model. It shows within, I think, 48 hours so it's 48 hours out that you can look at an event of what the weather's supposed to be. But like some of them have their quirks to where, like the NAM is a medium range. It tends to be a little aggressive to where you are looking at soundings and seeing what kind of environment that this system that's coming into, what potential it has to be severe. And I'll show you some of the data just seems to be a little out to lunch. So like surface temperatures and surface dew points. You could look at an event to see if it's going to be favorable for severe weather, and you go, okay, it's showing on the NAM that the surface temperature is going to be 80 degrees and the dew points are going to be into the mid-70s. And then you were to look at, for that day, let's say it's Friday, and then you were to go look at the National Weather Service's website and look at what the temperature is forecasted for Friday, and they might say it's going to be 74 degrees, and the dew points might be in the high 60s, but not in the 70s. So then you have to go back and go, well, I don't know how much I can trust the NAM because it's a little out to lunch. It's showing higher temperatures, higher dew points. The numbers are showing a little bit more aggressive than what some of the other models are and what the National Weather Service is showing forecasted for that day. So that's what makes forecasting the weather so tricky, is that you have to go in between these models and just kind of find a happy medium and then look for what seems to be crazy. Another thing that they're just doing this over and over and over again, that people have gotten, meteorologists that cover the weather and look at these models have gotten good at, is that there's also things that, depending on what time of year it is things that can change the outcome of what the models are showing versus like, well, I don't know if I believe all that. And like dew points, right? Dew points, moisture coming from the Gulf and coming into the U.S. You could look at a few different models, and one model might show that the dew points are into the 70s, and it's widespread in the southeast, and it's making it all the way into, mid-Michigan. The dew points, the 70s dew points are making it all the way into Michigan, and then coming all the way down, covering all of Kentucky, Alabama, Florida, Georgia, Mississippi, Louisiana, Arkansas. You might look at another model and it's showing the dew points are more of a thin line. It's not a giant area of real estate. It's showing a thin line, and it's maybe making it as far as halfway through Indiana, halfway through Illinois, and then coming down and spreading out. You might look at another run and it's showing a real small area of 70s dew points, rich, that rich moisture from the Gulf, and it's only making it to Mississippi, Alabama, Georgia, Louisiana, and halfway through Arkansas. So then you would think, you watch these models enough, but you know what time of year it is, you go, it's springtime. I just don't see that rich moisture making it all the way to Michigan for being like early springs. I just don't see that happening. So that's when you have to go back and forth between the models, but also make like, I know what time of year it is. That seems a little wild to see moisture that far. So I don't think I can really trust this model completely, because it's showing crazy rich moisture making it that far into the U.S. I just don't believe it. So that's Another thing that makes forecasting so tricky is that you really have to bounce around between a lot of the models to make an assessment of what seems a little out to lunch, what seems a little crazy. I don't know if I can trust this model. This model looks a little bit more realistic, and that just makes it hard. It makes forecasting the weather hard. Is you have to decipher through a lot of stuff. These are called soundings that I'm about to show you, and when you're looking at soundings for an environment, you want to look at the sounding of the environment before the storm gets there, because you want to see what the atmosphere is like for this sounding. If you take a sounding while the simulated reflectivity, while it shows the convection in that area, the environment is starting to stabilize. So you can't really trust the data that you get from a sounding if you take it in an area where there's already storms forming or happening on this forecast model. So was this New Hampshire? I can't think. I don't know the East Coast states that well. I can't remember. But this would be a sounding that you take while it's raining. You're taking a sounding of the environment while it's already raining, and you can see here that this atmosphere is already becoming stable. It's already saturated from the convection from the storms. And you see on here these little red lines. This is called a skew-T, by the way. This has your wet and dry adiabats. And just to keep this simple is that this is just showing how saturated or dry your atmosphere is for this environment. The green is your dew points. This blue dotted line is your storm parcel, and the red is your temperature. Down here below is your temperature, surface temperature, and then obviously going up from the 1000 millibar, the surface where we're at, going up into the air. So this is in degrees in Celsius. So you've got -10, -20, -30, -40, -50 degrees Celsius. Same way, just positive, 10 degrees, 20, 30, 40, 50 degrees Celsius. This on the side here is your wind barbs. It's showing the wind profile of this environment. I don't pay attention to this too much, but yeah, this is showing it's 54 loose matches SARS, 56% tornado down here. And what it's just saying is that there's 54 loose matches of similar soundings that looked like this, similar data as this, that had outcome of where it did produce a tornado. But like I said, when you're looking at soundings, you want to make sure you take a sounding before the storms hit. You don't want to do it while the storms are in this area. So you look at a sounding. Yeah, here's the one that's not in. This is the same area, roughly the same area, but this is one that's where there's not storms happening yet. This is ahead of the storms. So you see these red lines. It shows how tainted or corrupted that the data is. So when you take a sounding, you want to do it before the storms get there, because when the storms do get there, it's going to show that the environment is already starting to become stable. On the right here is called your hodograph, and in knots, in distance and height, this is just showing your wind profile. And what do you want for a tornado when you're looking at the winds is rolling. You want rolling with height in the winds. And these wind barbs match this. You see the colors down here, how the color's going up. It matches the wind profile on this. So it shows that you do have some rolling with height. And what we talked about earlier, right motion versus left motion, you have a right motion storm vector. So this storm shows down here. I don't know how easy it is to see this. It bunkers right at 259 degrees, 24 knots. So it's a storm. It's a right motion storm. So that's already checklist one of the potential that it can produce a tornado. Is it's moving the right way, and it's got rolling with height. So it's got veering with height or rolling with height it's a decent photograph that could have tornado potential. That's even if this event, because this is I think this was like a week. This is July 1st, so this is a few days, just a few days away. It is a potential outcome. Down here is your cape. It's showing your mixed layer cape. The mixing I was telling you about earlier, where you get buoyancy from the storms, the heat rises, gives these storms lift, and then they're rising through this cool air faster, and it's causing mixing. This is showing this environment of the mixed layer energy, which is 1,300 joules per kilogram. Most unstable is just adding everything in and showing your most unstable convective available potential energy. You have other things, values on this sounding. Convective inhibition, which is how, like, statistically in this sounding, what could hamper or cause a storm to not be as severe. What could inhibit a storm from being severe or the outcome. So it's got that values on it. Also on this, that's showing your storm parcel. It's showing your cape. Here's your cape between the temperature and the storm parcel itself. So not an insane amount of cape, but anything over 500 joules per kilogram of cape is enough. It's really on the low end, but it is enough for still a tornado to be possible. You have here, it shows down here, your LCL, which is your lifted condensation level. You have your LFC, which is level of free convection. So that is the level at which storms will still have buoyancy without stuff like the sun helping give buoyancy and energy to these storms. It's a level of free convection. So this is the level at what the storms are going to be able to climb without added energy. All right, down here too, you have your cats. You have down here you have your wind shear, storm relative helicity, meters squared per second squared. Storm relative helicity is just updraft. It's showing how much potential updraft that this storm has. And the effective inflow layer of 149 meters squared per second squared, or 24 knots. That's decent inflow, decent helicity, storm relative helicity. That's decent updraft for the storm to have the potential for tornadoes or just to become a severe thunderstorm. From where we're at, the surface to 1 kilometer above our head, wind shear in knots, we have 23 knots. And in the surface to the 3 kilometer above our head, we have 26 knots of wind shear, low level winds. I found out that pretty much anything as low as like 20 knots, 25 knots, like anything 20 knots or above in those two levels they're enough wind shear for a tornado. They're on the weaker side, but that is enough wind shear, low level winds for a tornado to be possible. So like I would say for a minimum, for Cape, your energy levels, 500 or higher is enough potential for tornadoes, and in your wind shear, from the surface to 1 kilometer above our head or surface to 3 kilometers above our head, anything around 20 knots or higher. So obviously if you have 50 knot wind shear at the lower levels, that's a lot of wind shear. That's definitely a way higher potential for a tornado to be possible. Other things on this sounding that you can look at, this is a storm slinky. I've watched a video on this before. It's just in a slinky form showing what the storm is doing or the wind profile is doing. Same way to this, it's just in slinky form is a hodograph. This is showing your juiciest part, your most moist part of the storm in energy, but this is not in joules per kilogram. This is measured in kelvins. So the unit of energy or unit of measurement in energy is kelvins. And then this is just showing with height, storm relative wind versus height. It's showing if it's more of a classic supercell shape or if it's, not a classic supercell shape. This, like I said, just shows your potential hazard type, tornado. And down here, like I said, if you've ever seen Facebook posts where they talk about the SARS analog system is showing that there could be an above average or an above tornado potential in Tornado Alley or in Dixie Alley or in the Ohio Valley or Tennessee Valley. This is just all the data that they've collected over the years, and then anytime there's a sounding where everything on this chart is similar to what has happened in the past. So this is showing a supercell. I don't know the year. Maybe it's July 3rd, 2011. This similar type of sounding produced a weak tornado. And then down below it says 75 loose matches. SARS 51% chance tornado. So there's 75 loose matches. Those 75 loose matches that where maybe things were a little different than this, just a little, that still had the potential for a tornado. It also shows hail. It shows okay, now I think I might have the year wrong, so it might be 11th of June 2003. This is showing severe hail. A similar type of sounding like this on July 17th of 1994 produced 1.25 inch sized hail. July 28th, 1989 day produced 1 inch hail. 19th of June 2000 produced 1/4 size hail. So it's 72 loose matches. SARS 19%. So 19% there was a significant hail. So this is just showing like other soundings that are like this, that the outcome that they had, so the outcome potential that this can have. That's why it's showing that tornado potential hazard type. I think in the comments that I'm going to put, not on this YouTube video that I'm making, but on if I post this on Facebook, I'm going to put down in the comments on the post, if you want to learn more about understanding these and reading these than what I explained to you, I'm going to put in links of people that I've watched that I learned how to understand these models. So if you want to learn more about this, you can click on their pages, you can go through their stuff, and they have guides to where they really in depth explain all of this. They explain this chart so it's, when you're looking at it, you're just like, what are all these squiggly lines? It's, you know, I've given you a little taste of what this is, but if you really want to know in depth everything on here, I can give you links to videos if you want to learn this, if you care. Which I know a lot of people are just like, no, no thanks. I understand. No, no hate. All right, now I'm going to talk about the radar and show you a few images that'll help you, hopefully help you if you decide to watch the radar, to look for severe weather coming your way and to look for tornadoes specifically, to see the rotation or the just what a better look at what a velocity couplet looks like and a debris signature from the correlation coefficient. This was a tornado that happened in Mississippi, Tylertown, Mississippi, earlier this year, and you kind of have the supercell itself blocked off from this tornado warning, but this, I think, caused two tornadoes, one that came through and another one that came right behind this one in Tylertown, Mississippi. But you can look here and you can see that this is like the classic tornado supercell shape. You have your wall of rain out ahead. You have your inflow, the storm inhaling that, you know, it's ingesting that hot humid air. It's pulling it in. It's feeding off that fuel. And it has the outflow. This little tail here is the outflow of the storm. But where this is at is where the tornado would be on the ground. And then if you go to the correlation coefficient, you see in the blue circle, this big blue circle is a debris signature. So that's what I'm saying. Earlier in the video I said it's tricky. It is tricky looking at the correlation coefficient, trying to figure out if something's on the ground or not. But sometimes, you know, you see all this color is kind of blended and then this blue sticks out. That's the debris signature. You know, it's tricky because you can get and I don't even know if this is like radar, like saturation or data corruption or something. I don't know what this is. I don't think I've asked, which I could probably do research and ask and figure out what this stuff is. But sometimes when you're looking at storms, you'll see a lot of this, and you might see a little blue in a mix of this, and it's tricky. It's complicated, and like it's something I'm still trying to learn more. There's just times where this is like a red and white, a black and white thing, to where it's like that's a debris signature. I see rotation. I see a velocity couplet. I mean, the storm had its supercell shape. That is your classic supercell tornado shape, and then it matches where the rotation is that's definitely debris signature. Another thing that makes that makes this tricky, and also seeing velocity and stuff, is the radar is at a tilt. What it picks up is at a tilt. It's got different tilts. So when you're looking at the velocity, sometimes you can look at different tilts to maybe see rotation further above or rotation a little bit closer to the ground. What makes it hard is when you have, like I said earlier in the video, the beginning of the video, is when you're really far away from the radar. It's kind of hard to decipher exactly what's going on because it's just so far away. Other things that can make it hard to read the radar is mountains. You have a radar looking off into the mountains, and storms are happening in the mountains, but maybe the mountains are really tall, and what the radar is picking up is hitting the side of the mountain, and it can't see what's happening. It can't see what's happening in between the mountains. So when you look at the data on the radar, it's really funky, and it's missing spots. So that's another way that's hard to tell and read the radar if there is a tornado happening, or like what the storm is doing in general, because you can have stuff like mountains blocking the view. Here's another example of, like I said, being in the mountains. So this was a tornado that happened in Tennessee, and I honestly can't remember if it was the springtime this year or if this was last year around the fall, late fall. I can't remember. But anyhow, you see all this missing data through here. Here's lightning, that's showing lightning strikes. All this missing data when the radar is trying to pick up what's happening in the mountains over here near Wartburg, Sunbright, Tennessee, heading towards Oak Ridge, Tennessee. Here's the correlation coefficient of where the debris signature would be, and you see how it's completely different from the previous photo I showed you. You just see this little bit of blue, and then you see the little kind of a mesh of yellow and maybe a little bit of maroon mix with out of this big scan. So it's hard. Like I said, it's tricky trying to find out if there is a debris signature or not, and what it looks like. Here's another example of, you know, a black and white. There's not a kind of gray area of trying to figure out on the correlation coefficient. Right here you can tell. This is your tornado warning. This was an observed tornado somewhere, Island City, Kentucky, and this is your debris signature. So it's pretty clear. You know, you see this blue debris ball. You don't see a mesh of other like yellow mixture in the lines and stuff. So this is a pretty easy way to go. There's a tornado on the ground by using the radar. And sometimes there's not always a red and green couplet on top of each other when you're looking at the velocity to see if there's rotation. In like QLCS linear systems that form like this, you look at the velocity, you might just see a line, a little line that maybe looks like there's a few little circles or maybe almost like divots in the line. I don't really know exactly how to explain it, but these are the kind of storms that can also produce quick spin-ups. So if you look, you don't see any red and green on top of each other. It looks like this whole system is moving still fairly in a straight line from one area to the next. So it's really hard to tell if is there rotation with this, or is this moving in a straight line fashion. You go to the correlation coefficient, even here, while it's moving, it still doesn't look like anything sticks out too much. But a closer look, you see this little ball here. This caused a brief, real brief, I don't think it did any real damage either, in London, Ohio, between South Charleston and Cedarville. Very tiny debris signature, and it's really hard to tell. Like that's another thing that you'd look at and go, was there anything on the ground? Did this form anything on the ground? But it did, and it was really short and brief. Here's another clear black and white, you know, night and day example. It's just, you can tell right away. Here's your debris signature, big blue ball, some little green colors around it too, but you can see out of this mixture that this is a pretty big debris signature, and it's easy to tell. Like right away you can look at that. If it matches with the velocity, then you look at the correlation coefficient. You can go, that is a debris signature. There is a tornado on the ground. Now when you look at velocity on the radar, this is a real easy telltale sign that there's rotation, and like I'm pretty sure this did produce a tornado, but this is what it looks like on the velocity. This is like strong rotation. You see big red hook and a big bright greenish hook where it's showing that rotation. The storm is rotating like this in a counterclockwise fashion, and I mean that's high. The brighter the color, the stronger the velocity. So the stronger the momentum in the rotation is.
Velocity field, which shows winds as detected by the radar beam. And when we do that, we look very closely for what's called a couplet. A couplet shows an area of rotation within a thunderstorm, and here's how it works. In a radar's velocity analysis field, red means the air is moving away from the radar dish, while green means the air is moving towards it. The brighter the red or green color, the stronger the detected wind is. When a small area of bright green and bright red appear right next to each other, that can indicate rotation. However, bright red next to bright green is not always a couplet. Sometimes it indicates a microburst, depending on the location of the colors in relation to the radar site. Plus, if we see an area of bright red or green by itself, that would indicate strong, straight-line winds. It's important to note that a couplet simply shows rotation aloft. Remember, that radar beam is thousands of feet up in the sky, so a couplet doesn't guarantee that a tornado is on the ground. Instead, it's a tool we use to identify where a tornado may be, and the National Weather Service uses other radar products to decide whether or not a warning should be issued.
So there you have it. It's a little bit about the radar, and that was a good little short video. But yeah, I've learned a lot. I've always been interested in thunderstorms. I've always remember as a kid opening up the window and looking outside and watching the lightning. I try to catch. Anytime there's a severe thunderstorm down here, safe if I can safely, I try to film it and record it, and I post it on YouTube. So I've learned a lot, and it just goes to show, like, you don't need to go to school for everything. Some things you can learn on your own. I think being a meteorologist would be pretty cool, but at the same time it would be a pay cut. So I'm just sticking to it as a hobby. But like reading the radar and understanding it isn't hard. Like I said a couple times in this video, if you watch it enough and you just watch the storm motion, you go, that is clearly rotating. And like, now is the rotation getting tighter, or is it still really broad rotation? Is this trying to maybe produce a tornado, or what? But if you watch it enough, you realize that it's not that hard. And you just pick up on stuff. You watch anything enough, you tend to pick up on things if you pay attention. So if you made it all the way through for this long video, and I hope you learned a bunch of things about meteorology and weather. There's still a lot more that I could explain, but I don't want to make this like a 10-hour long video. Yeah, on my YouTube channel, like I said, anytime there's a severe thunderstorm warning, I go outside and film it, as long as it's not producing a tornado. I'm always glued to the radar, and that's not just my house. Like anytime Michigan has severe weather, I'm looking out for what the severe potential is like over there. Anywhere in the U.S., anywhere where any of my family lives too, I'm watching the weather for their area, and I'm giving a heads up. Hey, tomorrow could be bad, or hey, you got a pretty gnarly looking storm coming your way. They might tornado warn it. Jeez, 80-mile-an-hour winds, damage threat, destructive, severe thunderstorm. That could be a microburst right there. And then if you look down here, you can see rotation happening here too. So you watch it enough, and you can clearly pick up on what's going on. This is in Missouri. So I hope you enjoyed the video. If you made it all the way through, I hope you learned something. In the comments, I'm going to post a bunch of storm chasers, meteorologists that cover the weather that I watch, and people that I've learned a lot on forecasting the weather and looking at stuff like the photographs, the wind profiles, and the storm behavior. Appreciate it.